Hello, this is Dr. Charles Conrick, Charles, and this is a discussion of continuing on the Amazing Spreadsheet Part 2. And what we're going to be discussing today is volatility. Now, on the spreadsheet that you're given with the book to use crystal ball to predict uh, the probabilities of doing well or whatever probability it might be on a particular trade, I would like you to please recall that, in fact, I'm going to go ahead and highlight this cell in a different color simply because of how important it is. And I've highlighted it in brown. In fact, it might be smart for me to even highlight there, historical volatility. Let me reiterate what exactly that means and the importance it plays on what we're trying to accomplish in estimating probability spread trading, and then what is the best way that perhaps we can go about putting a real number there. Again, I remind you that everything I say or do is not to be taken as truth, or that, oh yes, if I do this, everything is guaranteed and it guarantees performance and probabilities. Nothing could be further from the truth, and certainly all risks that you take by making a particular trade are yours and yours alone. I'm simply providing scientific data, evidence, and some results of studies that I've done. So a little bit of a disclaimer for you. But please take away from it what you can. Now, we already talked about annual return. Now, that's going to be up to you or me. And if we're dealing with a weekly spread, say a 5-day trade, the annual return reflects, well, what do I think is going to happen with this trade on an annual basis? This asset, this stock. Let's talk about SPY, Sierra Papa Yankee, the Standard & Poor's Index ETF. If I think it's going up 20%, well, I'd mark this up to 20% annually. If I think it's going down by 10% annually, I would put in a negative 10%. Since I don't know where it's going, particularly on a week-to-week basis, I generally will simply leave it at zero. So, I mean, that's a good assumption. It's going to neither go up or down. I don't know what it's going to do. I'm more interested in how it's going to vary around the expected return, which my best expected return is probably what it is right now, which the S&P closed on Friday, December 20th, 2013, at about 181.54, I believe it was, or 181.56. Now, we have two parts figured out. So this one is on you, whether you're using technical analysis, fundamental analysis, or your best guess, or the magic 8 ball. Whatever you want to put in there, I'm really not interested in covering with you. That's you can get from other sources. The price, of course, right here, item 3 is what it is. The starting price is what it is. Implied volatility is a function of what the option price is at a particular point in time. So for an example, if I was interested in playing a 5-day option trade right now, today is December the 21st, it's a Saturday, I'd have to wait till the market open on December 22nd, which of course we're getting into Christmas week, but getting away from all the holiday business, I can go and pull up an option chain, and in fact we'll pull up the 1227 chain and take a look. This is an option chain off of E-option, and as you can see, on the left-hand side are the calls, and the at the money calls are right around at 181.50, and on the right-hand side of the blue middle line, these are the strikes, are the puts. So the in the money puts are above 182, and the in the money calls are below 181.50. Let me caution you not to look at the moment the SPY J. Those are the jumbos, 10 times a normal trade. The SPY 7s are the mini options. We're looking at simply where it says SPY. And I can show you right now that at least as of close on Friday, the pricing, here's your ask and here's your bid price on a call. Here's your bid and ask price, and you're getting such. This is actually kind of a poor example, and I'll tell you why. The reason is because these prices are reflected closings and would be much closer during the course of a normal business day. So, without getting crazy, I'm just trying to show you where to find them. But right here on the far left-hand side, where I've got my cursor, I'll cursor up to the right-hand side, it says IV, implied volatility. What's the implied volatility of an at-the-money call? Well, if its ask price is $1, that would be 9.07%. That's the implied volatility. Now, does that mean that's the actual volatility? Answer no. Answer no. So going back to the spreadsheet for a moment, what I'm trying to suggest to you, and I think many of you probably already know this, is that I can look up the price. So if I put in a 181.50 put and put in about, I can't remember what it was, but let's go back down to about 9% volatility implied. We should be looking at about 76 cents on a at-the-money put. So if I go to an at-the-money 181.50 put, the implied volatility is showing at about 6.9%, which would give $1.07. So if I go back to the sheet, and in fact, that's crazy because that wouldn't work. I'm a little bit confused as to what. Again, those must have been closing, pardon me, $1.07 put would be an implied volatility of 12%, which is probably more realistic. Here's the point. The way implied volatility is derived is simply by taking the price on a normal market opening, when the market's open, a normal trading day. What is the market price of the option? And if you know the market price of the option, you can back in or figure out the implied volatility by solving for it in the Black-Scholes model, assuming that you know the interest rate that you're going to be using on the risk-free rate, the strike on the particular option that you're using, and then, of course, the time to expiry. So we were looking at a 5-day to expiry trade. According to this, the put was costing $1.07, but these were closing prices and might be thoroughly, in fact, I'm looking at the SPY 7. Here's the SPY, and it's trading at 80 cents, 7.3%. Let's plug that in. 80 cents, and let's see what we get for that. And I think you'll see what I mean here in just a second. If I plug in 80 cents down in the bottom corner right in here, the implied volatility is about 9.5% using the Black-Scholes model. So I'm a little unclear as to what how they're coming up with 7.3.1%, unless it was simply they're simply using some type of an average. I'm a little bit unclear. Please forgive me. I'm just trying to give you an example. But the actual way on real live trading would be very, very close to that spreadsheet that I'm showing you. In other words, if you plug in the price, if we plug in the price, I'm trying to find my cursor. Where did it go? I don't know. Evidently it's there, but I'm darned if I can. There it is. Okay. On a 181.50 put with 5 days to expiry, could be that they were using 7 days to expiry, which is probably what was happening. Let me just see for my own edification. And I have to change them both, evidently. Oops. Yeah, that could be it. Yeah, now we're getting much closer. Maybe you're seeing, I don't want to spend all your time talking about that. The point is that once you know this, the price, we use the implied volatility to make the price what it is. So we solve for implied volatility is what the market says it is. It really hasn't a whole lot to do with what actual volatility is because nobody knows what the future is. And then, of course, we've talked about interest rates. I leave mine at 0.5%. It's actually a little bit lower than that right now. But for that's not going to have that big of an impact. The strike price is whatever we pick, and time is computed. But going back to the main theme here, historical volatility. That's what we're predicting is going to happen over the future of the trade. And we don't know what it is. We have to shoot in a best guess. But to compute actual probabilities, to compute real probabilities, we have got to, as much as anything else, perhaps more than anything else, plug in our best estimate for what historical volatility should be. All right, so that being said, we can certainly look at the past. And this happens to be a spreadsheet that I have available to me, and I think I might have shown it to you. This is data from February of 07 all the way through close on 12/20/2013, and it shows the up and down weekly volatility of the market of the SPY. And what I'm showing you here is in fact, let me just back up a little bit here so you understand it. The mean change in the SPY over that almost 6-year time period has been virtually one tenth of 1%. A little bit more upside than downside. But look at the standard deviation, which is right here. Widen this out so you can see. Standard deviation, 3%, 2.99. So in the 1.8 standard deviation, what we have found is that, first of all, this chart is highly skewed, which you can see right here. This is a chart of all of the 6 years of data. And you can see between plus and minus 1.8 standard deviation from the mean, the blue line being the mean, and the red lines being about 1.8 standard deviations. You can see virtually all of the trades closed within that time frame. In other words, are closed within that gap. So obviously, the essence of what we're doing is trying to trade spreads out in these areas in the far hinterlands, where hopefully the market's not going to bother us. And if we can sell the credit spreads and increase our probability of winning, then in effect we can put a lot of money on the table. So let me ask you this: when you go to Las Vegas into casinos to play a game of, say, cards, blackjack, whatever. Let's say poker, so we all understand it. And if you got just a normal hand, like maybe a pair of deuces and a pair of fours, you're going to assess that and really be, if you had the book right in your hand and a computer in your brain, what you'd say is, well, my odds of winning are 60.2% or whatever it might be. And that would regulate your betting. But now if you pulled with no wild cards, if you pulled 4 aces, or better yet, if you pulled a royal flush, where your odds of winning are 99 and 100, I think you'd bet the house. So what we're talking about is a situation of estimating this volatility such that if we can put a large trade on, even though we're making a small reward, we're using casino theory. All right. That's the theory and a little bit of pictures so you can see it. Now, the question gets to be, all right, how do we best predict this? Now, I made a statement in the last session where I told you that, well, the VIX gives us one indicator. So what I'd like to do at this point is to pull up some hard data for you. And in order to do that, I need to get back to my home screen. So let me do that real quick. Like, I'll minimize all these. And I created some, that's the wrong one, I beg your pardon. I created some sheets that I would like you to look at. Let me get rid of about the website for you here. This sheet here, once I load it up, is using SPSS, the Statistical Package for the Social Sciences. What I've done is load up 20 years worth of data. In fact, let me make this a little bigger so we can all see it clearly. And I ran several tests on it. I sorted it for outliers, and I'm looking at 5-day, 10-day, and 20-day average historical volatility. So the 5-day volatility, the 10-day moving average volatility, and the 20-day moving average volatility, with the independent variable being the VIX, the VIX. All right. So you've got that. Let's take a look at this. I ran two tests, the tests being strictly linear regression and then a power regression. A power regression means that instead of just a straight line, I might be better off by saying that I think that the VIX exponentiated to a certain power would be perhaps, in other words, there might be a curved function. And since I've only got 30 minutes, I want to get to the point here. On a 5-day regression model, using the VIX as an independent variable, and a linear regression, I'm showing an R squared of 87%, which means that the VIX does explain a lot of the variance in the movement of the 5-day model. The test on an analysis of variance, for those of you that are academically minded, is significant. And most important, here's the really important thing. What does that mean? Well, that's telling me that if I take the VIX and multiply it by 0.697, or about 70%, it'll give me a good estimate of the 5-day average volatility. The power test was much better, showing an R squared, which means how much of the variance is explained by the VIX in the actual 5-day volatility. It comes out to be 95%. Now, what this means is that if I took the VIX, this means the log normal of VIX. If I took the VIX, let's say the VIX is at 10, and I exponentiated to the 1.28 power, so 10% exponentiated to the 1.28 power. Like you all know, 10 squared would be a 100, right? Well, in this case, I'm taking 10 and exponentiating it to the 1.28 power. You can do it on an Excel spreadsheet or any advanced calculator that has an exponentiation function. So take 0.10 and exponentiate it to the 1.28 power, and you'll get an estimate. And it'll be closer than the just taking the rough percentage. You might wish to try that. This is generally what I use. And there's the diagram. Now, that looks like a mess. Actually, it looks like a bunch of dots and two lines. Well, the black solid line is a straight linear regression. In other words, how do I best represent the derivation? And then you can see a dashed dotted line. That's your linear regression. Excuse me, curvilinear, the power regression. It's right up here is labeled the power regression, which actually bends and curves with the data. You can kind of follow along and you can see it bends and curves. Now, these are the highest R squared I received on the tests. And then all the little dots represent, well, where did the VIX measure up against the 5-day? And obviously there is a lot of error, but on the other hand, the power regression is explaining a lot of the data. For that much, so is the linear regression. I did the same thing with the 10-day. Got an R square on the linear regression of 93%, and the coefficient was 73%. So if you take the VIX, multiply it by 73%, you get a pretty good estimate of what the forecasted actual volatility is. You'll notice the R squared was about 98% on the power regression, and that exponential is 1.22. And then finally on the 20-day, there's your diagram chart of VIX functions versus actual volatility being on the left side, VIX on the right side, or on the horizontal axis. On the 20-day, the linear function gave us a 95% regression. The coefficient was 76% on the 20-day volatility. The power regression gave us a 98% estimation with a exponential of 1.18. Now, let me summarize this very briefly for you. What this means is, if you think about it, on the 5-day, the 5-day average, if you take the VIX at the close of a business day and either multiply it by about 70% or exponentiate it to the 1.27 power, you get a good estimate of the 5-day actual volatility according to history. past data. On the 10-day, just to refresh your memory, on the 10-day, the measures were, let's just look at the 10-day real quick. The 10-day was 73% of the VIX, just using a straight linear regression, and the power regression was an exponent of 1.22. And then the 20-day was the 20-day was 76% with an exponentiation of 1.18. Okay, now I'm done with that chart. Please feel free to watch this again if you wish. That's totally up to you, of course. Be happy to have you do it. I'm trying to open up another chart. These are the means. I wanted to point them out to you. Let me just show it to you. This goes back 20 years, but I neglected to tell you, I'm sorry. I did get rid of outliers. There was a bunch of outliers in the data, which just made it unpredictable. When I deleted outliers, I got rid of about 300 data points. Not quite, but almost. So I'm basing my data on what I consider to be the most representative data. In other words, under normal conditions. And the 5-day average, let's look at the mean score. The 5-day average over that whole time was about 13%. The 10-day average was about 14%. If I can find my cursor, I'll put it right in front. There's 14%. The 20-day was close to 15%, and the VIX over the 20 years was running at about an average of 19%, which backs up what I just said insofar as the VIX is actually a little bit, if you will, overstated compared to what has been shown to be actual data. So do I think this is absolutely guaranteed to give you perfect information? No, that's not what I'm saying at all, and I hope you don't think I am. What I'm suggesting is to you that what we can look at is, well, how do we figure out this information? Now, I had one other chart I wanted to show you. Regrettably, I'm not seeing it at the moment, so I guess I'm going to just skip past it. But let's go back to that chart sheet, this one here, and I'll expand it so you can see it. Keep in mind what we're looking at, and I'm going back to this indication, is that this is what actually happened over the past 20 years, and our job is to say, well, how do we actually plug in a historical volatility? That's what we're trying to figure out. Because if we can do that, and going to this chart, which you have an example of this in the book, but if we had known or had been able to guess over the past, this happens to go back to 07. This is about 6 years of data, updated all the way to 12, 20, 13. If we had actually known what the Standard & Poor's Index was going to do in any given week and stayed within plus or minus 1.8 standard deviations, heck, you can just count. 1, 2, 3, these are close, but they don't penetrate. 4, 5, this is in the crash of 2.8. 6, 7, 8, 9, 10. And then on the top, we have 11, 12, 13, 14, and at least using this rough estimate. Out of approximately 350 data points, a little bit more than that actually, you have 14 penetrations. So 14, 14 divided by 357 is, I'm going to make sure that I'm counting those distribution data points correctly. Bear with me. It's actually, yeah, it is 357. So 14 penetrations divided by 357. That counts up to about 3.9% of the time. 3.9% of the time, 357 divided by 14. Again, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10, 11, 12, 13. Sorry, I miscounted, but it's still going to be very close. 13 divided by 357 gives me about 3.6%. So 97 point some odd percent of 97.5% of the time, we are not going to lose if, capital if, we can correctly predict what the next 5 to 30, whatever you're playing, whatever trades you're playing. So this chart is showing me the historical records of, and you can see it right through December 20th, of what the VIX was, which is right here, the 20-day log normal, average historical volatility, the 10-day, and the 5-day. Another way would be to use crystal ball. And I'll close the session out by saying, all right, what is another way we can predict this? Keep in mind, I've showed you one already. One would be to take the VIX as an independent variable and use the VIX because that's what the market is guessing. Like right now, yesterday on December 20th, 2013, check your records, the VIX closed at 1379. So using that as a predictive variable, what I'm suggesting to you is, all right, what would you base your estimate on? Well, something you could use would be to say the 70 to 80% range. Somewhere in that range would be your best estimate using historical data. If you want to use the exponential power, for an example, if we take the 0.1379 and we exponentiate it using Excel to the 1.27 power, I would predict to you on that basis that the 5-day, I'm using the 5-day figure. In other words, 1379 exponentiated to 1.27 power, the historical volatility will be just about 8.1%. So if I change this to a percent function, what I'm suggesting to you is that, yeah, there we go. The 5 days should be at about 8%. And then, of course, 10-day would be, if I recall correctly, that same number exponentiated to the 1.21 power. So if I exponentiate that to the 1.21, I'd be looking at about 9%. So these are estimates based on historical data and assuming that the data tells us anything about the future. Between 5 and 10, I'm looking at the VIX as a historical predictor. There you go. There's an estimate. So you might feel safe in using 8.5% over the next 5 days if you want to split the difference. If you want to be precise, over the next 5 days, I would consider 8% to be a good estimate. Now, let's take a look at Crystal Ball. What can Crystal Ball do for us? Crystal Ball has a function, and I'll be conducting many more courses in using Crystal Ball. But Crystal Ball has a function called Predictor, which is a time series analysis tool. Now that's another way of using the data rather than just guessing. Let me show you how that works. Let's say we use 30 data points. Why 30? Well, the more data points, it represents like a larger sample size. In other words, if I was polling the United States population on how it's going to vote for president in 2016, Republican or Democrat, obviously if I polled 5 people, I really don't have much of a sample size. But if I randomly pick about 15,000 people all around the country, randomly picked from all different demographic characteristics and geography, etc., I'd probably have enough data to tell you with almost 99% precision who the next president would be. It's a function of what is the power of your test. So if I use just 6 data points, 5 or 6, like the last week, I'm not really getting a good function. A rule of thumb is to use a minimum of about 30 data points. Okay, where does that come from? Somebody made that up. That's the rule of thumb. It actually has to do with the t-test, but I don't have time to get into detail. So if I go back 30 days to say, I'm looking at row 1724. If I go back to 30 data points would be going back to row 1694. And all I need to do is highlight the 5, 10, and 20 day, 30 data points. What I can do is go up to Crystal Ball, click on Predictor, and just take a moment here, and tell it, okay, it's got the right data points. The data is in columns. The top row does not have headers. Data attributes, I'll have it, it'll adjust for any seasonality and so forth. And it'll choose the best methods for us, which is really nice. All right, let's run it and see what we get. What Crystal Ball has done is to run a time series analysis over the 5, the 10, and the 20-day period. A couple of things I'm looking for. The Durbin-Watson statistic up here tells me if I have a tremendous amount of correlation, and the Thiel's U data score here, if it's less than 1, tells me that I have better than a naive forecast. A naive forecast means that you might as well flip a coin. Better than naive means that you're better than 50-50, that you're actually doing, you've got a better than naive forecast. And over on the left-hand side, it's telling me on the 5-day forecast, the 5-day was right at about 12%, and the prediction is that it's on a time series analysis. Let's just look at the next say 7 days, so you get an idea of what that's all. We'll make it 10 days. Over the next 10 days, that time series analysis using 30 days of data is predicting to me that it looks like volatility will be coming down to about the 10% or maybe even the 9% range. So it dropped again, popped up, and of course the reason this happened was last week we had the Federal Open Market Committee announcement, and we experienced a huge volatility swing. And I guess the time series analysis is telling us that, all right, it's going to calm back down now. We'll go and look at the 10-day, and then I'll conclude the session. On the 10-day average, basically have the same story. And the Thiel's U is less than 1. Durbin-Watson is around 2, which is where it should be. It was showing 11%, and then this big spike up, which was the FOMC, and now the time series analysis over the next 10 days is telling me it should calm back down again and come down to about 11. Therefore, I feel fairly comfortable in looking at about 9%. Now, what does this all lead to? It goes back, ladies and gentlemen, to this sheet right here. If we want to go in and make full use of our probability theory, the cells highlighted in brown, historical volatility, or maybe more accurately, I should have called that actual volatility predicted over the time of the trade. I don't care if you're making this a 365-day trade, it makes no difference. Or if you're making a 10-day trade, what I'm telling you is whatever I like trading the weeklies every five days. They expire every Friday, and it gives me a fresh new chance. This is the brown colored cell is probably your most, if it's not the most important, it's certainly one of the most important. I'm going to go ahead and say it is the most important, because if you get that number correct, or as correct as possible, you are making very, very precise probability estimates. That's what we're in business for. Okay. Now, I know I didn't show you too much of the amazing spreadsheet today. Actually, I did, because you were seeing all of the volatilities computed. And if you recall, the whole purpose of the book and what we're doing is called probability trading theory and probability trading estimates, and trying to come up with the best estimates that we possibly can. So going back to this chart and seeing us, especially these two in 2008, I almost discount those because obviously the market crashed, the volatility was gigantic. But our goal is to be in between the two red lines where the market is not changing as frequently as we might think it is. And I am suggesting to you, as I showed you on this chart, in fact, all you need to do is look. I even put right here between plus and minus 2 standard deviations, 96% of the time, just like I suggested to you, or I was showing you 97% of the time, the market's going to be trading in between those two red lines. You can see it for yourself. If you, excuse me, I just dropped a little microphone. At any rate, this works, and this is strictly probability theory. It has not. People can talk whatever. I'm not studying the Greeks. I'm not studying anything except probability. This is casino. This is casino trading, except that we are the casino. The market is going to do what it wants. We're not trying to predict anything. In fact, many people would have stayed out of the market last week with FOMC meetings coming up, and I wouldn't have blamed them. I was in, and I happened to luck out. Most of what happens to us, ladies and gentlemen, as far as I'm concerned, we cannot predict, and we certainly can't predict the market. And there's an old adage that the market will move in the direction to hurt as many people as possible. Our goal is to stay out of the way of the market. And the real science that I'm exploring here as an academician and as a financial analyst is how can I do that best? And I'm asking you to consider that. And if you wish to continue to join me as we're going a lot further than this, I'm going to close now, say thank you for watching. And remember, all of this whole last two chapters was to do nothing but to discuss what do we put in to where it says 9%. Thank you, and I'll see you in future courses.